Topic 8.5 is looking at acid deposition. You may more formally know it as acid rain, but deposition takes in dry and wet particulates, acidic particulates into account. What causes acid deposition? First, you need to understand that rainwater is naturally acidic, and it's naturally acidic due to the fact that the atmosphere has gaseous CO2. And so when that happens, as we have seen before, you can have H2O liquid absorb CO2 gas, and they mix, right? And that is going to create carbonic acid, which is a weak acid, and that is going to break down into H+ and HCO3. And remember, these are equilibrium reactions, so they do go back and forth. So it's not like it's constantly just making more H ions. Those H ions are going back to make the carbonic acid, so on and so forth. But due to the presence of this H+, even though in minute amounts, this causes our pH of our rainwater to naturally be 5.6. And as we understand from the pH scale, 7 is neutral. And so that means it is it's over a factor of 10 hydrogen ion concentration over neutral water for our acid rain. So we know if our natural rain is 5.6, well, what is acid rain? Acid rain are solutions that have a pH less than that of 5.6. So that means you have additional acids within that rain. Okay, so main contributors of those acids are going to be oxides of nitrogen, and we use NOx kind of as a symbol for NO, NO2, N2O, it's oxides of nitrogen, and sulfur. Now these guys are considered primary pollutants. That means they're going to be given off from a direct source like burning fossil fuels, incomplete combustion, something along those lines. But they are not the acid rain themselves. What happens are these two guys are going to go up and mix with that water, right? And they are going to create, through reactions of the water, acid rain. So acid rain is technically a secondary pollutant. It is a result of the interaction of these chemicals with water, which we'll see in just a little bit. So acid deposition can be wet or dry. If it is considered wet acid deposition, that means the acid is in the form of rain, snow, sleet, hail, anything of moisture, fog that comes from our sky. And it's going to fall to the ground as a precipitate. So if you look at our picture over here, right? So we get our pollutants, so SO2 and NOx, and they come from something in industry, because these really did not exist prior to the Industrial Revolution. Well, when they get up into the atmosphere, if they get high enough up into the atmosphere, they can get carried off. And as you can see, oxidation is going to happen to create these different acids, as you can see. So we have sulfuric acid, nitric acid, nitrate acid, so on and so forth. And as they mix in with clouds, they turn into aqueous acid solutions, and then they're going to fall to the ground. And they're going to fall to the ground as an acid rain, causing a series of effects, which we'll talk about later. Dry is when acidifying particulates. So that is, for the most part, particularly with sulfur. So when we are burning coal, we're giving off sulfur particulates. And the thing is, in that smokestack, there are actual particles of sulfur, sulfur oxide, so on and so forth. And those, because of their density, can fall directly back onto the ground. And they're going to sit there. And then it's going to rain on it, or the moisture in the ground is going to interact with it, and it's going to turn into an acid at that site. So there's two chances of acid deposition. you will see the dry deposition occur a lot closer to the source of wherever the particulate came from, whereas acid rain can travel up to 1,500 kilometers from the source because it gets into the high atmosphere and moves with the water. And that's why it's a lot harder to depict wet precipitation and the source of wet precipitation. But dry particulates, we can backtrack to the source pretty readily. So looking more specifically at sulfur oxides. Sulfur oxides can be produced from coal, heavy oil, and so that's considered oil that, not what you would put in your car, but more of the kerosene type of oil, and smelting. And so when you burn coal, you get that characteristic smoke out of the smokestack. Now, most days there are things put into place that the smokestack's only steam and not particulates, which we'll talk about later. Smelting is when you have the melting of metals, and those metals tend to carry a lot of sulfur, and so the steam given off will have a lot of sulfur particulates in it. So what happens? First, you have to have the oxidation of sulfur. So that means when you have sulfur and it reacts with the oxygen in the atmosphere, that is going to give you your sulfur dioxide. It is colorless, but it has a smell. It's a very recognizable smell. This is your primary pollutant. Then, once that gets up into the atmosphere, it's going to interact with water. And when it reacts directly with water, it can make sulfurous acid, and that is when it has like most direct contact with water. So this type of acid could be made directly in the smokestacks for coal production or burning of coal and electricity production. But what is a little bit more dangerous is if we give that sulfur dioxide time to oxidize more. And so when that happens, that means it's going to react with oxygen again, and it's going to form sulfur trioxide. And when sulfur trioxide reacts with water, it's going to create sulfuric acid, which is stronger than sulfurous acid. Now, just a little bit about acid naming. So if you look here, we have SO3 and SO4. Sulfate is our traditional polyatomic ion. And so then you have sulfite, which is when you have one less oxygen right there. And so when you go and look at the acid name, sulfuric, ric means it's like standard form. Orous means that it is without, or it's one less oxygen. And so if you tend to have a polyatomic ion making an acid, so nitric acid would be regular nitrate, but nitrous acid would be -1. Phosphoric acid, traditional PO4. Phosphorus acid, PO3. And so you can use those suffixes to identify what type of acid you are going to be making. So there are several different ways that this can occur outside of just reacting with water. And so there's photooxidation, which means light is going to provide the energy needed to react sulfur and oxygen together. And that's dangerous because there's always a lot of light. There could be oxidation via metal particulates, and this one's a little bit more dangerous, or not dangerous, but more common when there's smelting occurring because those metals are present. Otherwise, this could also be present for dry deposition. If there are metals in the soil and surfaces that the sulfur is landing on, could react with those metals and then move forward with the reaction of becoming acidic or have acidic properties. And then of course there's free radicals of ozone and H2O2. So this could occur if, like, especially with ozone, that can occur if it gets up into the stratosphere. But the problem is a lot of our smog today, due to cars and all the pollutants that are released, we actually have a lot of ozone closer to the surface. So there's a lot more free radicals closer to the surface, which increases or compounds the effects of acid rain. So what this can look like is, we're going to use hydrogen peroxide as an example. So if we have a radical of hydrogen peroxide, and so if we react that with sulfur dioxide, you'll get a radical, or you'll get the combination between the radical and the sulfur dioxide. And then this is going to then go through oxidation, right? Because oxygen is present, and if you go back and look at the formation and breakdown of ozone, it's a very similar process. And then that's going to re-release a different radical and SO3. And then this SO3 can then go react with water and produce sulfuric acid. So there are several different mechanisms that can occur. And this could be the same thing for radicals of oxygen. It's a little bit more simple, because with ozone, the radical would just be O, right? And if that reacts with, SO2, you're going to get SO3 a little bit more directly, which then react that with water, and you're going to get H2SO4. So you just need to understand that not only can sulfur oxides react with water, but it can do it via multiple different mechanisms to make those acids. And so we have to know and understand what is in our atmosphere and what direction, and how that will explain how strong the reactions are going to be. Nitrogen oxides. They are produced from internal combustion engines. So traditionally what happens, because nitrogen is a very inert gas, so that means it does not readily react. But due to the heat of internal combustion engine, when nitrogen and oxygen intermix, which is going to happen because nitrogen is over 70% of just the gas in our atmosphere, so it's going to mix. That's going to create NO, or nitrous oxide gas. And to give you an idea, the delta H for this reaction is positive 181 kilojoules per mole. All right, so we know this is an extremely endothermic reaction. Therefore, we need the heat of that engine to push this forward. And so this particular gas did not exist prior to internal combustion engines. All right, another method, or another route that this reaction, another mechanism this reaction could take, is if we just change the ratio of oxygens and you get 2 NO2. All right, and that's the one we have to watch out for, is the creation of NO2. This gives off a brown gas. So that is that characteristic gas that's given off, especially with diesel engines, that brown blackish smoke. And so that haze, that smog haze you see over cities, that is this NO2. So what happens when NO2 interacts with water? Let's find out. So when that NO2 reacts with water, it creates HNO2 and HNO3. So HNO2 is -1 oxygen, so this is our nitrous acid, and HNO3 is our typical polyatomic ion, so that is your nitric acid. All right, so that is one way that can happen. Another way is if you are going to do two things. So you're going to react with water, but you're also going to have an oxidation reaction occurring at the same time. And that then will give you 4 HNO3. And so it all depends on what the situation, where molecules are at, to know which route. So just be comfortable with all the different possibilities that can occur. All right, and so this is the reactions with nitrogen oxides. Again, mechanisms, photooxidation, so light providing the energy to allow that oxidation to occur, just like with sulfur oxides. And then again, radicals. And so those radicals are O3 and hydrogen peroxide, just like prior. And so if we look, and using the hydrogen peroxide example, we have HO, and this is where this NO product comes from. And so if you remember on the previous slide, in the first reaction, N2 plus 1 O2 gives us NO. Well, that one doesn't directly react with water. What happens is if you have a radical present, then you get nitrous oxide. Well, that radical could also react with NO2 and produce nitric acid, right? Or you could have a free radical oxygen plus NO, and that's going to give you NO2, which then has the possibility of reacting with water, so on and so forth, and moving the reactions forward. So there's lots of mechanisms that this can take place. But essentially the take home is the more that brown smog you see, the more of the nitrous oxides. And the more nitrous oxides and the more brown it is, the more ozone is actually going to be present. And so you're going to actually have more ozone radicals, which then increases the chances of acidic rain in that area. And if you have a place like Denver, you can get something called an inversion, which means that air just sits there, because if we have hot air trying to rise and the cold air of the mountains trying to sink, things get trapped and you get that characteristic brown cloud that cannot escape, and which means you're increasing the amount of nitrous oxides and ozone, and therefore increasing the chances of creating really strong acid rain. Now you need to understand the impacts of acid deposition on materials. So marble or limestone, they are the same thing. It's just marble is more compacted limestone that has been going under metamorphic processes longer than limestone has. And so what happens when acid rain hits these particles, or marble or limestone, they actually start to dissolve. And you need to know the reactions that take place. So if you have dry deposition, so marble and limestone are made from calcium carbonate. And they're solid. If you guys didn't know that, they're a stone, they're rock. And so if you have dry deposition, that means you have sulfur dioxide landing on it. We do say it's in its gaseous form, but it can also be solid particles, but it tends to be actually a gas that just then falls and rests upon the stone. And then, of course, oxygen is going to be present for oxidation to occur. And so that's going to create a reaction called calcium sulfate and CO2. So bubbling actually occurs when you put an acid onto these guys. So that is one way. Because there's going to be moisture around, this is going to occur. If you have wet, so you just have your calcium carbonate stone, and it's going to get wet directly with acid rain. And you're going to produce calcium sulfate again. This time you'll have some water and CO2. Then you could also have that calcium carbonate reacting with nitric acid, producing calcium nitrate, water, and carbon dioxide. Now, what you need to know is calcium sulfate and calcium nitrate, these are soluble. So once before, with this carbonate, this is not soluble, which is why they can be in stone and why we can use that stone to build, because water's not going to dissolve it. But once you have that acid there to interact with it, it's going to create a compound that is soluble. Well, once that compound is soluble and you get a little bit of moisture, hence that water, that is going to wash the particulates away. And so here you can see with the stone, with her face, over time, it's getting eroded away. It's washing away because that calcium carbonate is turning into a soluble form of calcium, like calcium sulfate or calcium nitrate. The same thing can happen with metals and corroding metals. And so this is one way to do this is rusting. And so if you have iron, which we understand has the most effect due to rusting, and we have dry deposition, so SO2 is falling directly on it, and we've got oxygen to allow for oxidation to occur, you create iron sulfate, which has a reddish hue to it, which, as you know, which is rusting, sorry. You could have wet with sulfuric acid directly, and you're going to create iron sulfate and H2 gas. And again, because it's a sulfate, these are soluble, so they can slowly start being washed away. You could also do this with aluminum, even though it's a little bit harder with aluminum, but it can still occur. And because you're making a nitrate, nitrate is also soluble. So over time, you're going to get rusting. And then again, over time, it's going to start to flake off, and it's going to dissolve, and it's going to wash away. Impact on plant life. Because plants are really our first indicator that something is wrong with anything in our ecosystems. So if you start to see plants, they're going to have slower growth, so they're not having the growth rate they should have. You'll see injury, so bark changing color, holes in leaves, they look burned, and then of course it can lead to death. What happens, and the big issue, is a process called leaching, and this is a huge environmental issue. And so when acids interact with soils, and our soils are very important nutrients for plants, and then of course the plants uptake them, and then we eat the plants and get those nutrients because we don't directly eat the soil. Some of these minerals are magnesium, calcium, and potassium, which are trace minerals. Well, when they interact with an acid, just like with aluminum and iron previously, they now become soluble, and they're going to wash away, and that is the definition of leaching. Leaching means to pull out metals and wash them away. Another process, because they have that ability to pull out metals, well, aluminum's in the soil, and aluminum is actually toxic to life, period. Aluminum poisoning is very dangerous. Well, due to leaching, we're now pulling aluminum out into the soil, and that now makes it available for the roots to pull up, and that's going to cause a damage to the roots first, and then of course cause death of the plant. And so as you can see from these images, if you cause damage to the roots, the whole trees are going to die due to their inability to uptake water at that point. And then dry deposition blocks pores for gas exchange. And so if you have plants in humid environments, they're going to have more exposure. But here you can see that burning that takes place. And so when they block pores, you can't allow water and water to get in, CO2 to get out, and so on and so forth, but it can actually directly burn. And reason plants in more humid environments are at more risk, well, there's more exposure to wet and dry deposition due to the heaviness of the atmosphere. Impacts on water. First, it can create what's called dead zones. So that means the aquatic life is very sensitive, and it cannot sustain life under a pH of 5. Well, if our rain is naturally 5.6, a little bit more acid in that rain can severely change the aquatic life. Just like with plants, that's going to release aluminum into the water, which further lowers your pH because aluminum does act as an additional acid, which we'll talk about in 18.1 of why aluminum has that ability. And so here are all the current dead zones in the world. And look at the United States. We're in such a good spot here, right? And look at where the populations. So if you look at where population of life is, right, you're going to see an increase in the dead zones because you're going to have more power plants present, so on and so forth, allowing for that decrease. Well, just imagine what else can happen. Dead fish, dead aquatic ecosystems, fishing industries crashing, shrimping industries crashing. That has a huge effect that we have to keep an eye on. Now, you can return a dead zone into a living ecosystem again, like we've done with Lake Erie. Lake Erie was a dead zone due to all the pollution, but we have rehabilitated it and life is now back into it. We just have to be very diligent and cautious in what we're doing. And then eutrophication is when nitrates, which are present in acid rain or in fertilizers, period, and they get leached and washed away, they can over-fertilize water. So nitrates are what we call a limiting factor because nitrogen is one of the most important nutrients to a plant. Okay, and so it's limiting in water, which is why plants don't overgrow in water. But as nitrates are increased in water, now algae and plant species are like, yes, there's so much nutrients we can grow. This is going to create an algal bloom. And when algal bloom happens, it layers algae on top the surface of the water, so oxygen can't get in, and plants can't get sunlight, so they can't photosynthesize actively, and that's ultimately going to cause O2 depletion in the waterways. And that is going to then cause a dead zone. It's called hypoxic waters. So here is Louisiana and where the Mississippi flows out into the Gulf of Mexico. And all this green, those are algae blooms from fertilizers and acid rain that is happening, and that does spread out, causing a huge amount of issues in the shrimping industry for the Gulf of Mexico. Lastly, impact on human health. So dry particulates, they can be inhaled, and people with lung problems, especially with asthma, have more problems, but they can be inhaled, then cause asthma or cause an attack, or eventually actually give people some kind of lung problems and or cancer depending on where you live. And then the acid rain can cause corrosion of pipes because all our pipes are metal. And so when that happens over time, it's going to leach toxic metals out of those pipes, like aluminum, lead, or copper, depending on what your pipe is made up of. That then can be ingested through drinking or eating of foods, which is going to cause further problems in your body depending on which one you are taking in. So we are trying to go through and we're trying to reduce the emissions of our primary pollutants. So with sulfur, there are two types. There's pre-combustion and post-combustion removal methods. So pre-combustion is the removal or reduction of sulfur being exposed after burning the coal. So there's two processes. There's creation of metal sulfide. So they're going to crush the coal and wash the coal. Well, when that water is present, the sulfur in the coal and the water interact, and you're going to create a metal sulfide. That becomes heavy and it's going to be it sinks. And then we can pull the coal on top that's floating away and then take the metal sulfide and recycle it as needed. There's also hydrodesulfurization, also known as HDS. This is a catalytic process that removes sulfur from refined petroleum products. And so this one's not coal, this one's going to be crude oil. And it's going to create H2S, or sulfur hydride. And then we can actually convert that directly back to sulfur, which can be used in the production of sulfuric acid, which, as we had talked about in topic 7, is one of the most heavily produced products in industry due to the multiple uses of sulfuric acid. Just as long as it's not in the atmosphere, we're okay. Post-combustion, and this is where you can go through and you can fix the power plant smokestacks to help reduce how much sulfur makes it out of the smokestack, even though it's very expensive to do. This is the route most people are going. This can remove 90% of the sulfur in the coal smoke, which is a good thing, but it's very expensive to put in. But the way this is done is you have a filter made of calcium oxide, And so when that sulfur comes and interacts with that calcium oxide, you make calcium sulfite. You could also have a filter made of calcium carbonate. And when that reacts with sulfur dioxide, you make calcium sulfite and carbon dioxide. And of course, this isn't probably going to be our ideal choice. We'd probably prefer to use calcium oxide, but it's easier to get a hold of calcium carbonate. But either way, the reason the second one, we now create a greenhouse gas in addition. And so do we create more greenhouse gases, or do we allow acid deposition to happen? It's kind of a catch-22. Greenhouse gas is a little bit better because then we can do carbon sequestration and take that CO2 elsewhere. That's another story. But what do we do with these calcium sulfites, right? Oh, and there's another reaction, sorry. We can also take calcium carbonate we take that calcium sulfite and it gets reacted or oxidized with oxygen, and we make calcium sulfate. And you're like, well, that's how marble and limestone get eroded away. Why would we want to do that? Actually, this is a very important product, and it goes through to make plasterboard, which then can be made or used in construction processes. So what is awesome about this is we can take this pollutant, right? So we take this pollutant and we react it with a base. So these are actually bases, right? And we create this product, and we just oxidize this product, and we make out of this once upon a time pollutant into a usable product. And so it's kind of like recycling or using all our resources instead of wasting, which is pretty cool, I think. The reduction of our nitrous oxides, and that's why we put catalytic converters in cars. Yeah, okay, so what that does, catalytic converter. So one of the problems of catalytic converters is it does create carbon monoxide, but the whole point of that is to react with that creation from the internal combustion engine of NO. And the whole point of the catalytic converter is to then release CO2 and re-release N2. And so before, we were just releasing NO before catalytic converters, and that then, of course, went through and made acid rain. So we put a catalytic converter in. Now, in catalytic converters, we do release, if we're not careful, CO or carbon monoxide into the atmosphere, especially if there's not a lot of oxygen or refreshing of air, like in closed garages and stuff like that. But the whole point of the catalytic converter is for the incomplete combustion to react with the primary pollutant to acid rain to release CO2 and N2, which is better than releasing NO into the atmosphere. Again, we are releasing a greenhouse gas, CO2, but we do have methods that we can pull that back out of the atmosphere. So it's a catch-22. Do we increase the greenhouse gases, or do we get rid of acid rain? And then another idea, and this is more of advanced engines, if you could lower the temperature of combustion, then you don't hit that endothermic number of 181 kilojoules per mole that is required to create NO. And so you can, the formation of NO is reduced at lower temps. So what they're starting to look at is circulating the exhaust back into the engine, and so that the engine can use the heat from that exhaust to run it, so it actually is cooling the engine a little bit at the same time, and so that the ultimate exhaust that comes out is lower temperature, and ideally it would not hit that 181 kilojoules per mole and no creation of NO, which is a pretty cool concept. Then other options, we could just reduce our fossil fuel use. So make energy transfers more efficient, use public transportation, of course, go to renewable energy, not burn fossil fuels to begin with. And then, of course, restoration of ecosystems. So using that calcium oxide or calcium carbonate, lime or limestone, going through ecosystems who have been harmed and neutralizing it. So you neutralize acidic soils, you can neutralize water, and help return plant life and animal life and aquatic life. And that will then reintroduce buffer systems, which we talk about in topic 18. And so by reintroducing that buffer system, it will help absorb any other change in the acid rain that may come through every now and then. But the problem is, as we have degraded these ecosystems, their buffer systems have gone beyond capacity, and so they're breaking down. So by introducing calcium oxide or calcium carbonate, we're reintroducing the buffer so that any effect of acid rains will be dampened.